Today we are going to be looking at the counting principle and permutations. First, we're going to start with the counting principle. The counting principle we already looked at back in section 11.4. We used the counting principle to determine how many different events were going to be in our sample space. And we found that by finding a product. We found a product of the different ways that each of our different events could occur. So what we're looking at in this first example is we're going to be looking at some more uses or cases where we could apply the counting principle. So in example 1, a password is used to gain access to a computer account that is to consist of 2 lowercase letters followed by 4 digits. Determine how many different passwords are possible if. Right, and our first one, repetition of letters and digits is permitted. Right, so the first thing I'm going to do is I'm just going to kind of draw these out as we go. So that way we have a visual representation of what's going on. So we're going to have 6 different either letters or numbers in this particular password. Right? In this particular password, we're told that our first 2 things are to consist of lowercase letters. Right? And then our lowercase letters are to be followed by 4 different digits. Right? So looking at kind of the little map for this multiplication that we have here. Right? Once we have kind of planned out what we're looking at, how many different numbers that we're multiplying, then we simply just need to fill in the different numbers that we are multiplying. So thinking about our first 2, our digits are allowed to be repeated. So that means that we have 26 lowercase letters possible for our first entry in the password, and we have 26 lowercase digits possible for the second entry in our password. Right. As far as digits go, right, we can use digits 0 through 9. Remember that if we're talking about using digits 0 through 9, there's actually 10 digits, right? Because 1 through 9 would be 9 digits, and plus 1 more would be, for the 0 would be 10 digits. So we have 10 different possible digits that we could input into these last 4 characters of the password. Right, our counting principle says, well, once we have all of these different numbers, we're going to multiply them out. So we take 26 times 26 times 10 times 10 times 10 times 10, and that's going to give us 6,760,000 different possible passwords. Right, now the big difference between A and B, kind of our idea of with replacement and without replacement. So in example B, we're told that the repetition of letters and digits is not permitted. Right? So thinking about our letters, that means for our first letter we have 26 different letters possible in our alphabet, and then for our second letter, well, we have 25. Right? If we used, for example, the letter A for our first letter, we couldn't reuse it again, so we only have 25 to pick from. Right, our digits then, we have 10 digits for the first entry. If we use one of those and we can't reuse it, then we have 9, then we have 8, and then we have 7. We multiply these together, we get 3,276,000 possible passwords. So notice that by simply limiting the repetition, we've cut our number by a little more than half. Right? So we get a much smaller number as we're looking at this one. Right, so for C, we're still thinking about this password of 6 different characters. And we are told that our first letter must be a vowel. So our first letter, we have 5 vowels, A, E, I, O, and U. So we have those to choose from. The first digit cannot be 0, which we'll get to in a minute, and repetition of letters is not permitted. So that means that that vowel that we picked out for our first one, again, say if we picked A, we could not use for our second one, so we have 25 digits possible for that second character. Excuse me, 25 letters. As far as digits go, the first digit cannot be a 0. So that means that we have 9 other non-zero numbers to choose from. Right? Now, whichever one of those we just use, we cannot use again, but we are allowed to use 0 in this case. So let's say we picked the number 1 for our first digit. Well, we would have 0 and 2 through 9 left, which would give us a total of 9 digits for that second number that we're going to enter. Now we've used 2 numbers. Let's say we used 1 and 2, so we have 8 left. Now we've used 3 numbers, so we have 7 left for that last one. And then we're going to multiply these out, and in comparison we get a much smaller number. We only get 567,000 possible passwords. So the key thing to think about when you're using your counting principle is our idea of replacement, or in this case repetition. Can we use these things over again? Do we have other specific limitations on the number of choices that we have? And once we have all of those different values figured out, then we can go through and we can multiply them together. Right, down at the bottom of the page, we've got another example using the counting principle. It'll carry over to the top of the next page. In this example, at Old Navy, a supply of solid color t-shirts has just been received. The t-shirts come in the following colors: green, blue, white, yellow, and red. Billy Bragg, the floor manager, decides to display one of each color t-shirt in a row on a shelf. In how many different ways can he display the 5 different color t-shirts on a shelf? So here we have 5 different numbers that we're going to be filling in. So our first shirt, well, we have 5 different colors to choose from. Right? So let's say he picked the green one, then that was our first one. Right? So we want all of these to be different colors. So kind of like the ones on the previous example where we limited ourselves based on repetition, we're going to do the same thing here. So if we use one color in the first one, well, we have 4 left for the second one to choose from. Then we have 3 left for the third shirt, 2 left for the fourth shirt, and then the last one, well, we have no choice. We have the one question that, or excuse me, the one shirt that we haven't used yet. We multiply all of these together. 5 times 4 times 3 times 2 times 1 gives us 120 possible arrangements. So the use of the word different color t-shirts in here means that we cannot repeat the ones that we've already used. Right. If he wants to place the blue t-shirt in the middle, how many different ways can he arrange the t-shirts? So looking at this, again, we have 5 shirts. If he wants to place the blue t-shirt in the middle, well, we only have one option for that first t-shirt. Right, that means that that blue t-shirt has been used. We can't use it for the one on the far left. So out of the 5, we've already used one of them. So this means we're going to have 4 for this one. 1 less means we're going to have 3 for the next one. 1 less means we're going to have 2 for that one. And then our last one we only have one option for. If we multiply these together, 4 times 3 times 1 times 2 times 1 gives us 24 possible arrangements. Then in this last one, again, we still have 5 shirts. If he wants the white shirt to be first and the blue shirt to be last, how many different ways can he arrange the shirt? Well, that means that our first shirt and our last shirt are limited. That means if we've picked out and used the blue shirt and the white shirt, we only have 3 left. So we have 3 options for that next one, 2 for the next one, last color left, no option for that one, so we just have 1. And we multiply these across and we get 6 possible arrangements. So as you're going through and you're thinking about these problems with the counting principle, pay attention to whether or not things can be repeated, things can't. And thinking about, again, kind of tying into our idea of with replacement and without replacement that we've seen in previous sections. The other thing we're going to talk about in section 11.7 is we're going to talk about permutations. Permutation is an ordered arrangement of a set of given objects. As far as finding permutations go, we use what we call a factorial symbol to find permutations. So notice that our factorial symbol is this exclamation point. On most calculators, there is a way to get into your, even scientific calculators do have an opportunity or a button to do factorial, so you don't have to write it out by hand. Same thing is true with our other different probabilities that we're going to be looking at in the next couple of sections. And I will put kind of a more detailed description of some of these different things posted in Moodle as well to walk you through using these, doing these types of problems using a calculator. I will, since I'm not going to be using a calculator right now, show how you can also alternately work them all out by hand. So you don't necessarily need a calculator to do these. It will make a lot of them a lot faster and simpler though. All right, so in how many ways can 7 children be arranged in a line? Right, so this is an example of an ordered arrangement, right? Because we want to know how many different ways can they be arranged in a line. So who comes first, who comes second, who comes third, so on and so forth. So if we think about our factorial notation, right, that means that we have 7 different people. Right, so that means that for the first person in the line, well, we have 7 options. Then we had 6 for the next, 5 for the next, 3 times 2 times 1. And so that's what our factorial notation up above here means. Right? We're multiplying every number starting with that largest number that we have all the way down to 1. When we're dealing with permutations, one key thing to think about is that order does matter. All right, so we multiply all of these together. This gives us 5,040 ordered arrangements. All right, so we'll work through using a little bit more with our notation as we're going through this next one. So consider the 5 letters A, B, C, D, and E, and how many distinct ways can all 5 letters be selected and arranged if repetition is not allowed. So here we have 5 letters, we are looking at 5 factorial. Right? So 5 times 4 times 3 times 2 times 1 gives us 120 possible arrangements. Notice that B is slightly different. And how many distinct ways can only 3 letters be selected? So if we go back to kind of what we used for our previous examples, well, we have 5 for our first one, 4 vowels left, excuse me, not vowels, 4 letters left, then 3 letters left. And if we multiply these together, we get 60 possible arrangements. Now this difference between taking the full factorial and taking a smaller group from that is what we're going to be looking at in these next couple of examples on the next page when we're dealing with our different types of permutations in our permutation formula. All right, so our permutation formula, notice that it has a couple of different factorial symbols in here. Right, so this NPR that we see, right, a subscript of N and a subscript of R. N is the total number of objects that we have that we are choosing from. So if we're choosing from 5 letters, if we're choosing from 10 letters, right, that is going to be our N that we are looking at. Our R is our number of objects that are being chosen to put in this ordered list. So as we're going through these next couple problems, pay careful attention to the notation and work through these. Again, I will put an extra kind of tutorial of how to use the calculator to work through these problems on Moodle as well. So that way, if you don't want to work these out by hand, you can use a calculator to shorten the amount of work. In both the graphing calculator and scientific calculators, there are different probability functions, and that's where you're going to find these. All right, so we're going to use this formula above, and we're going to go back and think about the last example that we just talked about. Right, the last example, we had 5 letters, and out of those 5 letters, we were choosing and arranging just 3 of them. So instead of writing out our 5 times 4 times 3 and the 3 little spaces that we had written there, this is a perfect time for us to use this permutation formula. Notation wise, right, 5 is the number of objects that we're choosing from. Our P doesn't stand for probability, our P stands for permutation in this case. And then 3 is the number of objects that are being chosen. Right. Into our formula then, our n, our first number, we're going to put that factorial on top. So we put a 5 factorial on top. And then in the bottom, we're going to do n minus r. So in our case, 5 minus 3 factorial. So what we have here is 5 factorial. 5 minus 3 gives us 2 factorial. All right, so I'm going to go ahead and write these out just to show how we can kind of easily simplify some of these. All right. So 5 times 4 times 3 times 2 times 1. And that is our 5 factorial. And then our 2 factorial is 2 times 1. And then if we look at what we have left, we can cancel out our 2, we can cancel out our 1, and we're left with exactly what we had in that last part of example 4 on the previous page. 5 times 4 times 3, which gives us a total of 60 possible arrangements. So as you're working through these problems, feel free to use a combination of writing out each of your individual numbers that you're being multiplied together, using more along the lines of your counting principle, or use your permutation formula as you're working through these problems as well. All right. Example 5. You are among 8 people forming a skiing club. Collectively, you decide to put each person's name in a hat and randomly select a president, vice president, and a secretary. How many different arrangements or permutations of officers is possible? All right, so the number that comes before our P for permutation, right, is the total number of people in this case that we have. We have 8 people, right, and we are choosing 3 of them for different offices. So we have 8 factorial over 8 minus 3 factorial. So if we write this out, we're going to have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 up top. And then in the bottom, 8 minus 3 gives us 5. So 5 factorial is going to give us 5 times 4 times 3 times 2 times 1. And if we notice what happens, we get a lot of these to cancel out. Right, so we're left with 8 times 7 times 6, which gives us 336 arrangements. All right, example 6 is going to be very similar. Here we're looking at bike routes. The Prince George County Bicycle Club has 10 different routes members wish to travel exactly once, but they only have 6 specific dates for their trips. And how many ways can different routes be assigned to the dates scheduled for their trips? So we have a total of 10, and we are choosing a permutation of 6. So we have 10 factorial over 10 minus 6 factorial. Right. So looking at this, I'm going to kind of shorten out the amount of writing that I'm going to do. 10 minus 6 gives me 4 factorial. So in the denominator, I'm just going to write 4 factorial. And then up top, I'm going to write 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. Because the 4, 3, 2, 1 are going to be exactly the same in both of these. So we can cancel out those 4 factorials. Just means a little bit less writing. And then we're going to multiply this 10 times 9 times 8 times 7 times 6 times 5. And then we get 151,200 possible arrangements. right, the last example then that we're going to look at is we're going to look at permutations of duplicate objects. So the idea is here that we have different objects that may be repeated. So we're going to focus on different ways can letters be rearranged, but some of those letters in there are going to be repeated. So when we're dealing with this, our top number is still our factorial for our entire group. And then anything that's repeated, we're going to have those numbers as factorials underneath. So we'll kind of explain what this means. So if we look at this first example 7, in how many different ways can the letters of the word Bob be arranged? Right, so we picked a nice short word to start with. And if we think about this, we have 3 letters in Bob. So our numerator is 3. And then our denominator, well, if we look at what we have repeated, well, the B is repeated twice. So we're going to divide this by 2 factorial. Right. So what that's going to give us is 3 times 2 times 1 divided by 2 times 1, which gives us 3 possible ways. Now, the reason this is if we think about arranging these letters, we basically have 3 different combinations that can be used. Right? We can have Bob spelled correctly, B-O-B. We could have the 2 letter B's first, followed by an O, or we could have an O followed by 2 B's. Right? So thinking about these and looking at the repetitions, right? Since we have letters that are repeated, we don't get the full 6 options. We don't get the full 3 times 2 times 1 because some of the different entries get repeated more than once because of the repetition of letters. So for example B, we're going to look and see how many different ways the word Tallahassee can be rearranged. So first we're going to go through and we're going to count the total number of letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our numerator is going to be 11 factorial. And then we're going to divide it by anything that's repeated. Right? So first thing I notice is that my A is repeated. Right? So looking at this A happens to be repeated 3 times. So I'm going to divide this first by a 3 factorial. Then we notice that our L is repeated twice. So we're going to divide this by a 2 factorial. Right? And then we notice that our S is repeated twice. Our S is repeated twice, so we're going to divide this by another 2 factorial. And last but not least, we have 2 letter E's. So we're going to divide this by another 2 factorial. So anything that's repeated in our list of letters or numbers or whatever you happen to be looking at, we're going to divide by each of those different repetitions. Alright, so to make this one easier to work, I am going to write out all of our different factorials. So 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then down in our denominator, our 3 factorial is 3 times 2 times 1. Our 2 factorial is 2 times 1. Our other 2 factorial is 2 times 1. And then our last 2 factorial is another 2 times 1. The ones we don't really need to worry about because they are going to cancel each other out. So looking at these, this 3, 2, and 1 factorial. Right? I'm going to cancel those out with my 3, 2, and 1 factorial up here. Right? Again, these extra ones we can consider are gone. And if we look at what we have left, well, we have 2 times 2 times 2. 2 times 2 times 2 gives us 8. So then I'm going to cancel this 8 out, right, by multiplying all of those 2's together. 2 times 2 times 2 gives us 8. So then I'm going to multiply what I have left. Right? So I have 11 times 10 times 9 times 7 times 6 times 5 times 4, which gives me a total of 831,600 different arrangements. So when we're dealing with permutations and repetition of different letters or numbers or whatever we have to be looking at, we take the factorial of our total divided by each of the different numbers of repetitions that we have, all represented as factorials as well.